Right now, as you listen to this, your clock is measuring 1 second after another. That sounds like the most obvious sentence anyone could say. But according to relativity, there is no single clock ticking at the same rate everywhere in the universe. Somewhere far away, near a black hole, a clock identical to yours can accumulate less time than yours does when the two are later compared. This does not happen because the clock is broken. It does not happen because an invisible hand is dragging its gears. It happens because gravity is connected to the geometry of space-time, and time is part of that geometry. This is not science fiction. Gravitational time dilation is a measured consequence of general relativity. Its effects have been detected with atomic clocks, included in satellite navigation systems, and observed in relativistic signals from stars orbiting the supermassive black hole at the center of our galaxy. And once you understand why it happens, you may never think about time in quite the same way again. Here is the question this video will answer. If gravity is not a force reaching out and physically slowing a clock, then why does a clock closer to a massive object accumulate less time than a clock farther away? By the end, you will understand why time passes differently at different gravitational potentials, why a distant observer and a falling astronaut describe the approach to an event horizon differently, and why the answer forces us to abandon one of our oldest assumptions about the universe, the idea that time flows at the same rate everywhere, for everyone. Let us begin with why this question matters. Black holes are often treated as cosmic monsters, objects so extreme that they seem disconnected from ordinary life. But the physics that describes time near a black hole is not a separate kind of physics. The same relativistic principles matter for the clocks carried by navigation satellites. If engineers fail to account for relativity, satellite navigation positions would accumulate large errors over time. A black hole does not introduce a new law of time. It reveals an existing law under extreme conditions. Understanding time near a black hole means understanding something about time everywhere, including here, including now. To see why this is strange, we first need to be honest about the intuition we carry with us. Most of us grow up imagining time as a universal river. It flows at the same rate for every person, every planet, every clock, regardless of where they are or how they are moving. In this picture, a second on Earth is exactly the same as a second on the Moon, a second on a spacecraft, or a second near a black hole. Time in this intuitive model is the stage on which the universe performs. The events may change, but the stage itself does not. It simply exists, ticking forward independently of everything happening inside it. This intuition is not foolish. It matches almost everything we experience in daily life. Two people can synchronize their watches, spend a day in different rooms, and meet again with their watches, still agreeing to an accuracy that is more than sufficient for ordinary life. Nothing in everyday experience suggests that time could depend on where you are or how you move. That is precisely why Einstein's insight was so radical. Relativity did not merely adjust a small detail in physics. It changed the role of time itself. A useful way to picture the new idea is to imagine space and time as parts of a single structure called spacetime. But this picture is only a metaphor. Spacetime is not literally a rubber sheet floating inside a higher dimensional room. The precise statement is that mass energy determines the geometry of spacetime, and that geometry determines how freely falling objects and light move. Clocks follow paths through spacetime, and the amount of time measured by a clock depends on the path it takes. That locally measured time is called proper time. This changes what gravity means. In Newton's description, gravity is a force acting between masses. In general relativity, gravity is described as the curvature of spacetime produced by mass energy. A freely falling object is not being pulled through space by an invisible rope. It is following the natural path available to it in curved space-time. That description does not mean gravity is unreal. It means that the geometry of space-time is the more fundamental description in general relativity. Once time is part of space-time, the consequences become unavoidable. If the geometry of space-time can differ from one place to another, then the relationship between clocks can differ as well. Clocks at different gravitational potentials do not accumulate exactly the same amount of proper time when their paths are compared. This effect is called gravitational time dilation. A clock deeper in a gravitational well runs more slowly relative to a clock higher in the gravitational field, provided we specify how the two clocks are being compared. The effect is not a mechanical malfunction. Every observer next to their own clock sees it behaving normally. The difference appears when the histories of the clocks are compared. The effect is small on Earth, but it is real and measurable. Satellite navigation systems provide one practical example. Clocks on satellites experience both gravitational and velocity-related relativistic effects. Because the satellites are higher above Earth, Earth's gravitational field is weaker at their altitude, which makes their clocks run faster relative to clocks on the ground. Their orbital motion produces the opposite effect. Moving clocks run slower relative to stationary ones. The system must account for both contributions. Without relativistic corrections, navigation errors would grow rapidly, reaching the scale of kilometers over time, rather than remaining within the accuracy expected from modern positioning systems. Relativity is therefore not merely a theory used to describe distant black holes. It is part of the timing system behind technology used on Earth. There are also direct laboratory tests of gravitational time dilation. In the Pound-Rebka experiment carried out at Harvard in 1959, physicists measured a tiny change in the frequency of gamma rays sent between the top and bottom of a tower. Light traveling upward through Earth's gravitational field was observed to undergo the relativistic frequency shift predicted by general relativity. It is tempting to describe this as light simply losing energy while climbing upward. That shorthand can be useful, but it can also create the wrong picture. More precisely, observers at different gravitational potentials assign different frequencies to the same radiation. The measured shift is a manifestation of gravitational redshift and is related to the way clocks at different gravitational potentials compare. Later experiments used increasingly precise atomic clocks to detect gravitational time dilation over much smaller height differences. NIST and other laboratories have measured differences between clocks separated by distances on the scale of a building, a room, and eventually even smaller vertical separations. The lesson is not that time suddenly becomes strange, only near a black hole. Time is already sensitive to gravity here on Earth. A black hole simply magnifies an effect that is quietly present everywhere. Now we can ask what happens as an object approaches a black hole. A black hole is not simply a solid object with a surface. In the simplest description, it is a region of space-time bounded by an event horizon. The event horizon is a causal boundary. Once something crosses it, no future-directed path from that object can lead back outside the horizon, not even a path followed by light. The horizon is not a material wall. It is not a shell of matter waiting in space. For a sufficiently massive black hole, a freely falling observer could cross the horizon without encountering a local surface or an immediate physical shock at that exact location. That does not mean the journey is safe. The strength of tidal forces depends on how rapidly the gravitational field changes across the size of the falling object. Near a smaller black hole, tidal forces can become destructive before or near the horizon. Near a supermassive black hole, the horizon can be crossed, while the tidal forces there are comparatively mild, although they eventually become extreme deeper inside. Tidal stretching and gravitational time dilation are related to the same space-time geometry, but they are not the same phenomenon. Tidal forces describe differences in gravitational acceleration across an object. Time dilation describes how the proper time along one path compares with the proper time along another. Now imagine an astronaut falling toward a non-rotating black hole, while a distant observer watches from far away. From the distant observer's perspective, signals emitted by the astronaut take longer and longer to arrive as the astronaut approaches the event horizon. The light is increasingly red-shifted, its frequency falls, and its brightness decreases. In the common distant observer description, using the black hole's external time coordinate, the astronaut appears to slow down and fade near the horizon. This is why popular explanations often say that the astronaut appears to freeze. But freeze forever is an idealized shorthand, not a literal claim that the observer receives an infinitely long, perfectly visible image. The signals become increasingly delayed, stretched, and faint. In practice, the distant observer loses the ability to receive useful information about the astronaut's continued fall. From the astronaut's own perspective, the story is different. Their local clock continues to tick normally. Their heartbeat, thoughts, and onboard instruments behave normally at the horizon, assuming the black hole is large enough that tidal forces are not already overwhelming. In their own proper time, they cross the horizon after a finite interval. This is not a contradiction. The two observers are following different paths through space-time and are comparing events using different coordinate descriptions. There is no universal cosmic clock in the background that provides one master time against which every observer's clock is simply running fast or slow. The astronaut does not feel their own time slow down. The distant observer does not receive a live view of the astronaut's entire journey after the signals become unable to escape. Both descriptions can be correct because relativity does not require every observer to assign the same time coordinate to distant events. The distinction between local experience and distant observation is one of the deepest lessons of general relativity. A clock measures the proper time along its own world line. When two clocks are brought together again, or when their readings are compared through a carefully defined procedure, the difference between them can be calculated and tested. But asking which clock is really running slow without specifying the comparison is often an incomplete question. We can see relativistic effects in the sky as well as in laboratories. The star S2 orbits Sagittarius A, the supermassive black hole at the center of the Milky Way, roughly 26,000 light-years from the Sun. During its closest approach, S2 moves at several percent of the speed of light. Astronomers have measured relativistic effects in its orbit, including gravitational redshift and the relativistic advance of its orbit's orientation. These observations support the predictions of general relativity in a strong gravity environment. They are not a direct experiment in which a clock is carried through the event horizon. Instead, astronomers measure the motion and light from the star and compare those observations with relativistic models. That distinction matters. Science becomes stronger, not weaker, when we say exactly what an observation demonstrates. There is also a subtle point about black hole formation. Astrophysical black holes can form through the gravitational collapse of massive stars, mergers, and other processes that concentrate enough mass energy within a region from which no light can escape. Classical general relativity predicts a singularity inside the simplest, idealized black hole solutions. But that prediction marks a limit of the classical theory. We do not directly observe a material point of infinite density. For this video, the important fact is the event horizon. a region of space-time whose causal structure prevents signals from escaping to the outside. We do not need to treat the singularity as an observed physical object in order to understand gravitational time dilation outside the horizon. So let us bring the argument together. Time near a black hole does not slow down because an invisible hand reaches into a clock and drags its mechanism. It slows relative to a distant clock because clocks follow different paths through curved space-time, and the proper time accumulated along those paths can differ. A clock near a massive object is not malfunctioning. It is measuring the time along its own path. A clock farther away is also measuring its own path. When the two are compared, the geometry of space-time reveals itself through the difference between their readings. This means that the strangeness of black holes is not really about black holes alone. It is about the nature of time, revealed under the most extreme conditions in the universe. The same theory that describes the delayed, red-shifted signals from an astronaut near an event horizon also helps engineers synchronize satellite navigation systems. The same relativistic principles that affect stars near Sagittarius A can be tested with atomic clocks separated by a small height difference on Earth. Black holes do not create a new kind of time. They expose, with extraordinary clarity, a truth that is already present everywhere. Time is not a universal river flowing at one fixed rate for the entire universe. Time is local. It is connected to motion, gravity, and the geometry of space-time. It can pass at different rates along different paths, and those differences are not errors in our clocks. They are part of the physical structure of reality. That leaves us with another question. If space and time can curve around a black hole, what does it mean for the universe itself to expand? When cosmologists say that the universe is expanding, what exactly is expanding? And what, if anything, is it expanding into? That question will take us from the edge of a single black hole to the edge of everything we can observe. This has been Planck's Edge. Thank you for stepping past the edge of what you thought you knew about time.